Okay, so in experiments number 2 and number 3, you're going to actually be determining, the ultimate goal is to determine the amount of oxalate in your crystal. Starting with experiment number 2. The goal of this experiment is to standardize the permanganate that you guys made. Permanganate is industrially super, super dirty, and it's not going to be the molarity you made. What molarity did you guys make? 0.01. It's actually going to be less than that because permanganate is not pure. So before you start this, one of the things you need to do is make sure you balance this equation, and you need to balance it in acidic solution. The stoichiometry required for this equation is going to be necessary for the final calculations that you have to do. So you're going to start, and you're going to have, and I'll show you the slides in a second, but I want to talk about how this works. You're going to have permanganate in your burette, and you're going to measure out a set amount of sodium oxalate as prescribed in the lab. That you're going to dissolve, and you're going to titrate. Now this permanganate, this is a manganese of 0.7 going to a 0.2. What happens and how this works is the permanganate is purple, the Mn plus, because as y'all have seen that, right? When there's oxalate present, to reduce it, it's going to reduce to +2 with this colorless, which is colorless. So you're going to put in permanganate, and it's going to be colorless, colorless, colorless in the bottom of the beaker until you run out of oxalate. At the point you run out of oxalate, 1 drop of permanganate will make it a light purple color. That's the equivalence point when you have equal moles of the sodium oxalate and of the potassium permanganate. Okay? So that's the key to what's going on. There is no indicator here. The color you're seeing, that pink endpoint, is the Mn +7 because there's no more oxalate to reduce it to +2. So as far as how to do the lab, you're going to fill your burette, and you do have a little burette funnel that you can put in here. And you're going to then weigh out a set amount, and this is not necessarily exactly what you need. And you don't need to get exactly a certain amount. You just have to write down exactly what you used. You're going to write down in your data table how much sodium oxalate, and you're going to dissolve it in some water. This is not super, super crucial exactly how much water, just enough to get it dissolved. Then you're going to add sulfuric acid. This is the big one here because it's a redox titration. And what did I say? You're going to balance it in what? An acidified solution. So redox won't happen if you don't add the sulfuric acid. Currently, this is under the fume hood, and you're going to use pipettes to fill your little graduated cylinders up. Okay? Then you're going to heat this sample. Most of you have a heater magnetic stirrer combo. You're going to turn on the heat and the stir at the same time, and you're going to heat it. Your goal is to be at your endpoint between, or your equivalence point, between 60 and 70 degrees. So I say heat it up to about 80, and then start your titration. The titrant is going to cool it down as you add it. When you hit that 80 or 90, though, because you're on the hot plate, I would turn the heat off right when you hit it, and then continue with the stirring. And then get to that end point. At the end point, make sure you're between 60 and 70, and then you need to, if you're between that amount, when you have your pink color, you're done. If it dropped below, turn the heat back on and make sure the pink color stays until you get it back into that range. So it has to be pink between 60 and 70 degrees. There are a couple stations back there that we don't have enough hot plate combos. You have a hot plate and you have an actual stir. This won't get so hot that you can't touch the top of the Erlenmeyer, so heat it to the right temperature, move it to the magnetic stir, which will be underneath your burette, and then go. And then titrate, and then check the temperature again. If you need to heat it up, you can go put it back. One thing I want you to be careful of with this thermometer, do not let it sit on the bottom of the Erlenmeyer or the beaker. Does anyone know why? Because what? Well, that's a good point. The stirrer will hit it, but there's something more important. Not melt. What? Right. What are you actually measuring? Are you measuring the temperature of the solution? No, you're measuring the temperature of the glass sitting directly on the hot plate. So it's going to be hotter than it should be. So you just want to hold it kind of on in the middle of the water until you get to the right temperature, read it, and then take the thermometer out and place it on the side safely so it doesn't roll off the counter. Okay? So you're going to continue your titration. One thing that you're going to notice with this permanganate, it's very dark, and our burettes have brown writing, so it's going to be super hard to read. You're going to kind of have to just do your best looking at the graduation above it and kind of do your best to guess to 2 decimal places where your mils are. It is going to be hard to read, I'm aware of it, but it is what it is. You just have to muddle through it. The end point looks a lot like phenolphthalein, the equivalence point, but it's not. This is just 1 drop of permanganate that didn't get reduced. So it's going to be like that pink color. Now, as far as the ending goes, the calculations, one of the biggest mistakes is the difference in calculations between experiment 2 and experiment 3. In experiment 2, you're measuring out sodium oxalate. So that's the molar mass you use to find moles of sodium oxalate. And then for every 1 mole of sodium oxalate, you have 1 mole of oxalate. So there's an important thing right there. And I'll point out the difference in the other experiment when I get there. The other thing you need to watch out for, and this is kind of a hint to help you out, if your permanganate is about 0.01 and you use the appropriate grams, you should be hitting your equivalence point somewhere in the low 20s. So I say go fast to about 15 mils or so, and then slow it down. There is a crazy thing that goes on with this titration, and I've talked to a bunch of professors at the reading about it and all these different people, and the big thing is that this particular activation energy, when you start, we don't know if the activation energy is low or whatever, you're going to add a couple drops at the beginning, and it's going to stay dark purple, and you're going to go, oh, and you haven't even added like 3 or 4 drops at the beginning, you're going to freak out. Just let it sit. It'll clear up, and then you can continue your titration normally. Okay, so just be aware at the beginning, it's going to be crazy weird, but it'll get better. So in addition to finding the molarity, we're going to also find the percent purity of your original permanganate. So for that, you need, these are the grams, whatever, that you guys weighed out at the beginning. You have 3 decimal places. You're not going to have 4. Okay? So that's experiment 2. The purpose then of experiment 3, you're reversing. You're taking your standardized KMnO4 that you now know the molarity of. Maybe it's like 0.00970 or something like that. And you're going to take it and you're going to figure out the percent of oxalate in your crystal. So now this is the first time you're actually going to get to use your crystal. Once you've calculated your molarity, you're going to start experiment 3. This experiment is done the exact same way, but instead of the oxalate, you're going to use sodium oxalate. You're actually going to use your green crystal, and you're going to weigh it out. In addition to adding sulfuric acid, you have to add phosphoric acid. It's in the notes. If you read your procedure, you'll be reminded of that. That's important because this ties up the iron. That iron ion gets in the way of the endpoint, so adding the phosphoric acid keeps it out of the picture because we're not dealing with the iron right now. We're only looking at oxalate. So we're going to continue the titration, same exact heating, same exact look and endpoint, equivalence point, and here I want you to check out the mils are a little more this time. So I'd say go fast to about 25 mils. You should be hitting in the low 30s, so it's safe to go fast, 25. And then here's a big difference. This is where students screw up. When they're getting to where they need to find the moles of oxalate to convert to grams of oxalate, they use the same molar mass as they did before. You are not finding the molar mass of sodium oxalate because there is no sodium oxalate in your crystal. The only thing in your crystal is the oxalate itself. So use this molar mass to find grams of oxalate. Once you know grams of oxalate, you know what grams of green crystal you use, and you can find the percent of it part over whole. And all of this, just by reading down your data table and doing every single calc, it pretty much is telling you what to do. So I'm not going to go over that in detail. You can figure that out. I'm just pointing out to you that here you use just the molar mass of oxalate. Is there anything else in here? No, I think that's it. So I don't know. That's all. I guess I'm done. That's all I have to say till experiment 4 or 5. Come and ask me questions if you have any.